Good morning, good afternoon, good evening, wherever you are in the world, and welcome to the webinar. We're going to get started now. We've only got 30 minutes, so it's going to be quite punchy. We've got a lot of information to share, so we'll get straight into it. So welcome again. My name's Gavin Morgan. I am the head of Industrial IoT for CAD-IT, and joining me today is Andrew Howarth, our Senior IoT Application Consultant. You can see the agenda on the left. We're going to look at some of the business challenges around improving productivity and benchmarking equipment. And it falls into two categories where we're going to look at production performance and individual equipment performance and the relationship between those two. And then we're going to discuss how Industrial IoT helps with this compared to traditional methods of assessing this performance. And then I'm going to hand over to Andrew to give us a demonstration using an IoT solution. I should mention at this point as well, if you do have any questions, please pop them into the chat and hopefully we'll get time at the end to pick some of those up. If we don't get time, we'll definitely get back to you via email or something like that. Okay, so when we look at production performance, here we've got a graphic that represents a simple linear production process. Each operation will have a planned production time and there will be planned queue times in between each operation. And all this time added together goes to make the overall planned lead time for the product. So this planned lead time must be minimized so that manufacturers can keep costs as low as possible in order to remain competitive. So therefore, it's important that the actual lead time is as close to, if not equal to, the planned lead time. As you can imagine, manufacturing leaders are always faced with the challenge of understanding the delta between the actual and the planned lead times. And so to gain a better understanding, they must delve deeper into each operation to understand what's happening at that level and to see if there's anything that's contributing to the gap between planned and actual. So they need a way of assessing performance at an individual equipment level. So here we have our old friend OEE, or overall equipment effectiveness. And this isn't supposed to be a back to school lesson for anybody by any means, but it's probably the most effective way of understanding how a piece of equipment is performing and how effective it is compared to the plan, which in a perfect world would be 100%. Now you can find various different ways of calculating each element of the formula, but I wouldn't get too hung up on it. If you just select the best way that matters to your business and you stick with it to make sure you have a constant way of measuring it and track it over time, you'll be fine. So now, by having a reliable method of understanding equipment performance, such as OEE, we should understand where in our overall production process to target our improvement actions. So in this example, we can see that things start to drift off plan on the third operation. So our OEE is good at the first two operations, but we're starting to drift on the third, and then we've got a downstream effect. So we'd naturally look there first to make targeted improvements. But the problem still comes with the word that I mentioned a little bit earlier, reliable, having a reliable method of understanding performance. So let's just have a look at that issue of reliability of the data. If we look at each element in turn and start to understand why our traditional methods of collecting data have led to unreliable data sets. So availability is looking at the percentage of your planned production time that was spent producing. The issues that have typically been that the actual time quite often comes from a manual record, and this can be very subjective and relies very much on trust from people who are running the equipment. Unplanned losses are not always captured accurately, so we often get an inflated running time. And the planned running time tends to be the biggest area of contention. Different people have different views on what should or shouldn't be included in this aspect of the calculation. So by using an IoT solution and connecting the equipment to that solution, the actual running time can be captured and derived consistently and accurately from the equipment all the time. Moving on to performance, here we're interested in the ability to produce at the planned rate. So this is often measured by counting the number of parts produced in each period, such as a single shift or a 24-hour period, and comparing that to the production plan. So much like actual running time, the actual number of parts produced can come from manual paper-based tally charts, Excel spreadsheets, or people moving markers around on magnetic whiteboards in factories, which is all inefficient and subject to error. The planned number of parts should be in line with the plan from an ERP system, or at least the weekly plan that is flowed down from ERP that might be in Excel. So by using IoT, you could count the completed cycles via a connection to the machine, or even connect directly to an MES or an ERP system to grab that single source of the truth. Quality. This obviously refers to whether the parts that were produced were conforming to spec or not. And here is probably the biggest challenge. It's often the case that at the end of a production cycle, it's not known whether a good part or a bad part has been produced. Some exception to that would be if the equipment has built-in inspections, such as on machine probing. But perhaps the machine has crashed or experienced an issue and stopped early, which would be an obvious indicator of a defective part. Quite often we've got to wait for parts to be inspected further downstream, which makes the measure a little retrospective. So to tackle this, a lot of businesses set the quality measure to 100% as a constant, and then link the quality data back once it's available to get a true OEE. And just lastly on this, the quality data usually goes into some kind of siloed repository, making it difficult to link to the availability and the performance data. So by adopting an IoT solution, the data can be automatically collected and linked from the electronic data sources, making it more efficient and more consistent. So with that, that's the school lesson over. I'm going to hand over to Andrew now, who will give us a demonstration. I'll just make Andrew host. Over to you, Andy.
Okay, thank you, Gavin. Hello, everyone. So what we're going to do now is take you through a scenario of how OEE is used to investigate and solve a problem within a bakery process. Now, what you see here is an application called OEE Hub, which is part of the MindSphere Industrial IoT service solution. And you can see on the left-hand side, I've got a series of assets that exist within a bakery. So working back from this bakery, there are 2 finishing lines, 2 mixers, and there are 2 ovens. So what you can see at the moment on the bakery asset, which is kind of the parent asset over all the other production lines or baking lines, is an OEE score. So straight away, this becomes a really useful signpost to the bakery operations and management team of how the bakery is performing. In this example, it's taken an aggregation from the finishing processes, finish line 1 and 2, to see if they are producing the level of product that is required against their orders, and if the overall finishing line machines are available and whether they're producing the right quality. So clearly this is indicating there is a low OEE score against the desired score, and this is being driven by predominantly performance and quality issues. So you can see further down on here the trend over time on this particular day, and we can see across the statuses of the machines when the machines have been running and when they haven't. So the purple indicates a period of time where there is no planned production. The grey area is when there was no data being provided, so the machine is neither planned to be in production nor actually producing any data. And then the green area is a time when production is in operation. So the machine is running and everything is okay. A red area would indicate there is some unplanned downtime during a time when production is planned. Now this whole production calendar is fully configurable by the bakery or the business. So this provides flexibility in terms of how individual cells, production lines, areas plan to produce their product by having a calendar that's specific to that asset or to that area. So what we can also see here on this screen is a shift drop down, and what this allows us to do is switch between different shifts. So currently we are seeing the single shift used, which is day shift. But of course, if you had an early shift, you had an evening shift, you could start to look at the OEE across different shifts and compare if your OEE changes on different shift times. So a really simple filter across there. Similarly, we can switch between the order IDs to see if specific orders have worse or better performance. So there we have 89% OEE for order 1002, mainly driven by quality. But you can see here order 1001 has a slightly higher order OEE, but the quality is also quite low. But overall, on average, we're seeing lower performance than expected and lower quality. We can then switch between actual products. So here we've got a product called CK1, which is in the bakery situation, it's the cookie. And here we have a flapjack. And we can see again that the quality is low on the flapjack. It's also low on the cookie, but there are differences in the performance significantly, although both are on target. So in this scenario, in this investigation, we want to see what is driving some of these performance measures. And what we can do, we can work our way through these assets and have a look at what is affecting the OEE scores. So we're going to work our way back through the process and take a look at the finishing line. Just going to refresh my screen there. Okay, so here we are now looking at finishing line 1. And we can see here that finishing line 1 has a performance of 73% and quite a low OEE score. The quality is also 77%. When we compare this to finishing line 2, you can see a distinct difference. So we now know that line 1, the finishing line 1, is not producing the products it should, nor is it producing the conforming products. So there's a lot of waste and there's also a poor production rate. So we're going to step back a little bit further to try and understand downstream whether the other operation assets are producing efficiently as well. So we go back to oven 1 and we can see that oven 1 is actually producing the rate that's expected. And oven 2 is also producing slightly higher than oven 1, but well within target. So when we look back to the mixers, we can see that mixer 2 is producing well on target. However, now you can see that mixer 1 has both performance issues and availability issues. So how does this contribute to the overall OEE problems that we're seeing on the bakery finishing lines? So well, you can see now that we've got a number of unplanned stoppages. Now these planned stoppages are obviously affecting the rate of product that's being produced, but they could also be contributing to quality issues. So we've got a clear indication of how much downtime that is resulting in. So over 1.5 hours of downtime. So in terms of performance, we can drill down and see the rate of production over time. So every hour here in the blue graphs, we can see the rate of production was lower than expected against the orange line. However, there was a time when the production rate was caught back up a little because there was a lot more produced at this time, but then it started to flatline again. So what was happening around these periods and why are we not producing at rate? So I'll go and step back to the overview and we'll now look into the availability. So we can see here in the red areas, there was stoppages, unplanned downtime stoppages on the mixer 1, which is, we know, resulted in an hour and a half of stoppage. What was happening in these times? How can we ascertain what was causing those stoppages? Because still at this moment, we know the mixer is contributing to the performance issues, but we don't know why. So we have the ability to look further into the downtime reasons. So here I've got an overview of 2 different stoppage reasons. We have simply no product being available, but we also have motor faults. And this is showing that the motor fault is contributing to the majority of the downtime reasons. In this case, over 1 hour of stoppage. So at this case, you may want to have an engineer investigate why Mixer 1 is having motor problems, but we know this is contributing to the productivity issues. And it could also be contributing to the quality issues if this incident is occurring with the motor whilst the product is in the mixer. So we can step straight into the actual analysis of the time series data for that particular motor. And the engineer can have a look at the condition of the motor whilst that particular fault was occurring. So what we'll do here, we'll have a look at Mixer 1 and we'll look into the values for temperature and vibration. And you can see here we also have a status code. If I just look at temperature and vibration, I'm going to drill a little deeper into the time series analysis. And I'm going to switch on the event for when the mixer was running. Now I can already see there are spikes in temperature and vibration. But what I can now also see is these spikes are occurring when I'm being indicated there is a high motor temperature. So I have a status event being triggered from the motor, and this is correlating with high vibration and high temperature. So we've now got a reason for these stoppages, and we know there's a problem with the motor. So what we can do from this, we can set up further alerts from these temperatures and vibrations. So we are warned of when the motor is approaching an out of range temperature or vibration. So that when the motor is fixed, if it's likely to cause these stoppages again, we'll know about it before it happens. So a really quick way, an efficient way of being able to prevent these stoppages in future. But now we understand the source and the root of the problem. Okay, so that's a demonstration of how OEE can be used to first analyze performance issues within a bakery process, and then understand which asset is causing the performance issues, and then what it is on that particular asset that's contributing to the performance issues. In this case, some motor stoppages and motor faults that can now be fixed by an engineer, and furthermore, put some alerting in place so we can prevent these stoppages in future. Okay, so we'll now hand back to Gavin, I think.
Yep. Thanks, Andy. So you got an overview there of what I was speaking about at a sort of theoretical level. You got a view of technology being applied to help with the challenges there. The product we were using was Siemens' product called MindSphere, but there are other IoT solutions out there. So really, all that leaves us with is a few minutes to take any questions from the attendees. So we'll just go on mute for 2 or 3 minutes and give you a chance to pop any questions you've got into the chat. And then Alison, who's our moderator, will be able to pitch those questions to me or Andy. Okay, thank you.
Hi, Gav. So we've had one question come in already, which is, how is the data collected?
Andy, do you want to pick that one up?
Yes, certainly. So what I'll do, I'll just talk you through a little bit of detail about the options for collecting data, but then also how the application is constructed to make that data visible. So first and foremost, to make the data sort of reliable and consistent, as Gav sort of alluded to and mentioned earlier, when data is captured on paper or through lots of inconsistent means, the accuracy becomes difficult, the completeness can be poor, and as a result, the OEE measure becomes untrustworthy, or you simply can't compare machines or areas of the business. So what we've done in this case, we've connected some hardware, which is an IoT gateway, directly to machines. And from those machines, we can collect straight from the PLC or the HMI or the data storage source, the status of the machine, any faults and alarms, and if possible, the product that's being produced on the machine at the time. So we know the rate and what was being produced. As Gav also mentioned, if this data is coming from multiple sources, so one example might be an MES system that tells you what product's being produced on the machine, on the work center, and how many, but the machine itself will tell you the status. Those two data sources can also be pulled in together, and from that data source, we can then feed the OEE application. But just touching on the actual setup of the application, it's really important to highlight that the way this application is configured is quite simple. So as you can see on my configuration overview screen, there are 8 boxes. Now really there's only 7 that must be configured. So the quality code here isn't about the quality of the product, it's about the quality of the data. So in a lot of cases with data that's being supplied through industrial protocols, it's supplied with a quality code that means we can inform the system of whether that data can be trusted, whether it's complete or not. So that is optional to be configured. The rest is a simple step-by-step procedure on configuring your KPIs, all the way through to your time models, the reasons for stoppages, what the different statuses are from the machine and what they relate to, what products and product rates you expect, and then the calendar for production. And then these can all be associated with the individual machines and lines. So when I click on one of these, you can see there's lots of different KPIs, all used for feeding the visualizations that you see. The reason why this is important and why I'm sharing this is it is quite common that businesses might have subtle different ways of calculating some of the KPIs around OEE and availability. So it gives you the option to customize this to your needs, while still being able to maintain a consistent formula throughout your production operation. And as you can see, I'm now guided through all of the steps for configuring the different time models. So here we've got in production, we've got 3 different types of planned stoppage, 3 different types of availability loss. And then we can then create different reason trees. So this is different time categories associated with different states on the machine, and then different reason layers. Okay, so I won't go into too much detail on that, but really I just wanted to highlight that there's a lot of flexibility for ensuring that the data meets your production needs, but also meets the context of your business. Okay.
Thanks, Andy. We've got another question, which is, what type of sensors are available? What are the most valuable? You talk about vibration and temperature.
Yeah, so I can take that one as well. So
yeah, go on, Andy. Yeah.
I mean, there are a range of temperatures, of sensors available on the market, either from third parties or through Siemens. So vibration analytics sensors, some temperature sensors that can bolt onto a motor. What's important here really is the way that the sensors communicate. So if these sensors are directly plugged into a PLC and the data is being stored in the memory of the PLC, then what we do is we attach these hardware gateways that we spoke about to the PLC and read the data in. Alternatively, in some cases, maybe you don't want the burden of connecting the sensors to the PLC and it's purely about data collection. So there are options as well to simply stream that data directly into the gateway devices or wirelessly over the network. In both situations, whether they're hardwired to the gateway or to the PLC, or whether they're wirelessly streaming, there are a range of options and a range of industrial protocols that can be used for reading that data. It's quite a sort of diverse answer in terms of options, but it gives the flexibility there to be able to really deploy and scale quickly when you want to measure certain key process variables without necessarily having to integrate these sensors into your control system.
So Andy, if I can just jump in there and pick up on the question around what are the most valuable? Well, you know, that's a different answer for every different organization, I think. And what we would always advise is to go back to your process FMEAs or equipment FMEAs to understand what are the common problems that the process suffers from, or what are the common problems that the equipment suffers from. And therefore that will guide you to, you know, the right sort of sensor to be able to apply and connect to monitor those parameters to solve the top ranking issues on your FMEA studies. Okay.
And Gary, if I just might add to that, what we do see quite common is that the OEE metric, the OEE KPI, can act as a signpost to that decision-making process. So if you have an availability issue and you start to do the sort of deep dive discovery that I just sort of demonstrated, and you discover that you've got stoppages and issues, but actually you've gone as far as the data will take you, you don't have the level of insight you need to fully alert you or resolve this issue in future. The OEE can therefore guide you that because you've got availability issues and production losses, and you know the asset, and you might know one of the reasons why it might be happening, you can then use that to inform you what sensors to go and buy to improve that data set, so that the condition monitoring and the alerting that you need to put in place to avoid the stoppage in future can be done so, and you know exactly what it is you need to do.
Yeah. Okay. I can't see any more questions on the chat. And we're right on time. So thank you very much. Thank you for attending. Hope you found it useful. And we'll see you on the next one.